March 15, 1942, Akron, Ohio. The Goodyear Tire and Rubber Company's main production line ground to a halt as plant manager Harold Thompson stared at a telegram that would reshape American industry forever. Japanese forces had captured the Dutch East Indies, severing America's access to 90% of the world's natural rubber supply. In the span of 6 months, the Empire of Japan had systematically seized every major rubber plantation from Singapore to Sumatra, creating a stranglehold that threatened to paralyze the Allied war effort. Thompson crumpled the telegram, understanding immediately that the 35 million automobile tires his company produced annually had just become impossible to manufacture using traditional methods. Across America that morning, similar scenes played out in tire factories from Detroit to Los Angeles. The mathematics of crisis were stark and unforgiving. American civilian and military consumption required 600,000 tons of rubber annually. Strategic reserves contained barely 540,000 tons, enough for perhaps 9 months of rationed consumption. Germany, despite controlling no natural rubber sources, had been producing synthetic alternatives since the 1930s. America, blessed with abundant natural resources, had never seriously pursued artificial substitutes. The nation that could outproduce the world in steel, aluminum, and petroleum faced potential defeat through lack of a single critical material that grew only in tropical climates now controlled by enemies. The transformation that would follow represents one of history's most remarkable industrial achievements. Within 30 months, American chemists, engineers, and factory workers would create an entirely new industry from theoretical knowledge, constructing massive chemical plants that converted petroleum into synthetic rubber at scales previously considered impossible. The story reveals how wartime necessity drove innovation that continues shaping modern life 8 decades later. Every tire on every vehicle today traces its lineage to decisions made in corporate boardrooms and government offices during those desperate months of 1942. The crisis had been building since Pearl Harbor, though few recognized its implications initially. Natural rubber cultivation required specific tropical conditions found only in Southeast Asia and parts of South America. The Hevea brasiliensis tree, source of latex that became rubber, grew exclusively in regions within 15 degrees of the equator, where temperature, humidity, and rainfall maintained precise balances. British and Dutch colonial plantations in Malaya, Burma, and the East Indies produced over 1.2 million tons annually, representing 97% of global supply. American attempts to establish rubber plantations in the Philippines, Central America, and Brazil had yielded minimal results, hampered by plant diseases, labor shortages, and economic competition from established Asian sources. Harvey Firestone, founder of the Firestone Tire and Rubber Company, had spent decades warning about America's dangerous dependence on foreign rubber. His company operated a 1 million acre plantation in Liberia, established in 1926 after securing a 99-year lease from the Liberian government. Yet even this massive investment produced only 35,000 tons annually, less than 6% of American consumption. Firestone's congressional testimony in 1940 had been prophetic, but largely ignored. We are building our industrial might on foundations controlled by others. When war comes, those foundations will crumble, and American production will halt for want of materials we could have developed ourselves. German advances in synthetic rubber production provided both warning and hope. IG Farben, the massive German chemical conglomerate, had pioneered Buna rubber production during the 1930s, driven by Nazi Germany's autarky policies that demanded self-sufficiency in strategic materials. By 1939, German plants produced over 120,000 tons of synthetic rubber annually using coal-based feedstocks. The quality initially fell short of natural rubber, but continuous improvements had created acceptable substitutes for many applications. German military vehicles, aircraft tires, and industrial equipment increasingly relied on synthetic materials that performed adequately under combat conditions. American chemical companies had monitored German developments, but saw little commercial incentive to invest heavily in synthetic production, while natural rubber remained abundant and cheap. Standard Oil of New Jersey maintained research agreements with IG Farben that provided access to German synthetic rubber technology, but large-scale production required massive capital investments that seemed unnecessary during peacetime. The economic calculus favored importing natural rubber at 15 cents per pound over manufacturing synthetic alternatives at estimated costs exceeding 25 cents per pound. Pearl Harbor changed everything overnight. President Roosevelt's declaration of war triggered immediate reassessment of strategic vulnerabilities across American industry. The War Production Board, established just weeks after Pearl Harbor, identified rubber as the most critical shortage threatening war production. Leon Henderson, director of the Office of Price Administration, delivered a sobering assessment to Roosevelt in January 1942. Without rubber, we cannot build tanks, trucks, aircraft, or ships. We cannot move supplies or troops. The entire war effort depends on maintaining mobility, and mobility requires tires that we can no longer manufacture. The Japanese offensive through Southeast Asia proceeded with devastating efficiency. Singapore fell on February 15, 1942, followed by the Dutch East Indies in early March. Within 90 days of Pearl Harbor, Japanese forces controlled 95% of world rubber production. The few remaining sources in Ceylon, India, and South America could supply perhaps 150,000 tons annually, less than 25% of American requirements. Rationing became inevitable, but even severe restrictions would only delay the crisis, not solve it. Bernard Baruch, the elderly financier who had coordinated American industrial production during World War I, received appointment to chair the Rubber Survey Committee in June 1942. His mandate was simple but daunting. Determine how America could meet its rubber requirements without access to traditional sources. Baruch's committee included some of America's most capable industrial leaders, including James Conant, president of Harvard University, an expert in organic chemistry, and Carl Compton, president of MIT and specialist in industrial research applications. The committee's preliminary findings, delivered in August 1942, outlined the magnitude of the challenge. American stockpiles would support minimal civilian consumption and full military requirements through early 1944. Expanded synthetic production could bridge the gap, but only if massive industrial capacity was built immediately using untested technologies at unprecedented scales. The report estimated that adequate synthetic rubber production would require construction of 51 new chemical plants at a cost exceeding $700 million, equivalent to roughly $15 billion in modern purchasing power. More challenging than the financial investment was the technical complexity involved. Synthetic rubber production required converting petroleum-based chemicals through multi-step processes that had never been attempted at industrial scales. The basic chemistry was understood, but scaling laboratory procedures to produce thousands of tons daily presented countless unknown challenges. Each synthetic rubber plant would require integration of petroleum refining, chemical processing, and polymerization technologies in ways that had never been tested outside experimental facilities. The race began in September 1942, when the War Production Board allocated highest priority ratings to synthetic rubber plant construction. 4 major chemical processes competed for selection as the foundation of American production. Standard Oil's butyl rubber offered superior performance for inner tubes and gas masks. Firestone and Phillips Petroleum advocated for butadiene styrene copolymer rubber that most closely approximated natural rubber properties. DuPont promoted neoprene synthetic rubber that provided excellent resistance to oils and chemicals. Union Carbide supported development of specialty synthetic rubbers for specific military applications. Rather than selecting a single approach, the War Production Board approved parallel development of all promising technologies. The decision reflected both uncertainty about which methods would prove most effective and recognition that different applications might require different synthetic materials. The diversity of approaches also provided insurance against technical failures that could cripple the entire program if concentrated in a single process. Construction began simultaneously at locations across America during late 1942 and early 1943. The Phillips Petroleum Company broke ground on a massive butadiene styrene facility in Borger, Texas, designed to produce 90,000 tons annually. Standard Oil constructed similar capacity at Baton Rouge, Louisiana, while Firestone built integrated production facilities in Akron, Ohio. The plants required not only rubber synthesis equipment, but also the petroleum processing facilities needed to produce raw materials, creating industrial complexes that dwarfed anything previously attempted in American chemical manufacturing. The workforce challenges proved as daunting as the technical obstacles. Synthetic rubber production demanded workers skilled in chemical processes, high-temperature operations, and precision quality control that few Americans possessed. Traditional rubber workers understood latex processing and tire manufacturing, but synthetic production required entirely different expertise drawn from petroleum refining, chemical engineering, and polymer science. Training programs developed at major universities prepared thousands of technicians and engineers for jobs that had not existed before the war emergency. The first synthetic rubber produced in American plants during spring 1943 barely qualified as adequate. Workers at the Borger facility watched nervously as the initial batches emerged from polymerization reactors with inconsistent texture, unpredictable strength, and processing characteristics that confounded tire manufacturers accustomed to natural rubber's predictable behavior. Quality Control Supervisor Martha Henderson recorded in her daily reports that early synthetic rubber samples varied so dramatically in properties that tire molds designed for natural rubber produced wheels that failed basic safety tests. The learning curve proved steeper than anyone anticipated. Natural rubber possessed molecular structures refined by millions of years of biological evolution, creating material properties that synthetic alternatives struggled to replicate. The long polymer chains that gave natural rubber its elasticity and durability required precise temperature control, catalyst management, and timing that pushed 1940s chemical engineering to its absolute limits. Workers operated equipment that existed nowhere else on Earth, troubleshooting problems that no textbook addressed, developing solutions through trial and error that consumed precious time and materials. Dr. Frank Mayo, chief chemist at the Akron Synthetic Rubber Research Laboratory, documented the technical challenges in reports that revealed the complexity of creating artificial materials that matched natural performance. The molecular weight distribution of synthetic polymers determined everything from processing ease to final product durability. Yet controlling this distribution required monitoring and adjustment of dozens of variables simultaneously. Temperature fluctuations of even 5 degrees could alter polymer characteristics enough to render entire production runs unusable for tire manufacturing. The human cost of rapid industrial expansion became evident as workers struggled with dangerous chemical processes under tremendous time pressure. Exposure to styrene vapors caused headaches and nausea among plant workers. Butadiene handling required special ventilation systems that often failed to protect workers from chemical burns and respiratory irritation. Safety protocols developed for traditional petroleum refining proved inadequate for synthetic rubber production, leading to accident rates that alarmed government inspectors and union representatives. Despite these challenges, production capacity grew steadily throughout 1943. The Phillips plant in Borger reached half its design capacity by June, producing 35,000 tons of synthetic rubber that gradually improved in quality as operators gained experience. Standard Oil's Baton Rouge facility achieved similar progress, while smaller plants in Ohio, California, and Louisiana added thousands of tons monthly to national production. By December 1943, American synthetic rubber output exceeded 180,000 tons annually, still far short of requirements, but demonstrating that large-scale production was achievable. The breakthrough moment came not from any single technical advance, but from systematic improvement across hundreds of small details. Workers discovered that slight modifications to catalyst preparation dramatically improved polymer consistency. Plant engineers learned that precise timing of chemical additions prevented the formation of gel particles that weakened final products. Quality control technicians developed testing procedures that identified problems before they affected entire production batches. These accumulated improvements transformed synthetic rubber from laboratory curiosity to industrial reality. Military testing provided the ultimate validation of synthetic rubber performance. The Army Quartermaster Corps conducted exhaustive trials comparing synthetic and natural rubber tires under combat conditions. Vehicles driven across desert terrain, through tropical humidity, and over mountain roads gradually proved that synthetic tires could match natural rubber durability in most applications. The synthetic materials showed superior resistance to petroleum products and extreme temperatures, advantages that proved crucial for military vehicles operating in diverse environments. The civilian population experienced synthetic rubber's impact through rationing programs that allocated precious natural rubber supplies to essential uses while synthetic production ramped up. The Office of Price Administration issued tire rationing books that limited civilian purchases to one new tire per vehicle every 6 months, forcing Americans to recondition existing tires and drive fewer miles. These restrictions, while unpopular, bought time for synthetic production to reach levels that could support both military and civilian requirements. By 1944, the transformation was accelerating beyond all projections. American synthetic rubber plants produced over 350,000 tons, approaching the levels needed to maintain both war production and minimal civilian consumption. More importantly, the quality had improved dramatically through continuous process refinement and worker expertise gained through months of hands-on experience. Tire manufacturers reported that synthetic rubber increasingly matched natural rubber performance, while offering advantages in specific applications that natural materials could not provide. The economic implications extended far beyond immediate wartime needs. Synthetic rubber production required massive investments in chemical processing infrastructure that created entirely new industrial capabilities. Plants designed to convert petroleum into rubber could be modified to produce plastics, synthetic fibers, and other chemical products that would define post-war American manufacturing. The workforce trained in polymer chemistry and large-scale chemical operations provided human capital for industries that would emerge in subsequent decades. International competition intensified as other nations recognized the strategic importance of synthetic rubber independence. Britain launched its own synthetic rubber program, drawing on German technology captured during the war, while developing improved processes suited to British raw materials and industrial capabilities. The Soviet Union expanded synthetic rubber production, using coal-based feedstocks, achieving self-sufficiency by 1945 through methods that emphasized quantity over quality refinement. The Japanese response revealed the limitations of natural rubber dependence, even for nations controlling tropical plantations. While Japan possessed access to Southeast Asian rubber supplies, transporting raw materials to industrial centers became increasingly difficult as Allied submarines and aircraft interdicted shipping routes. Japanese synthetic rubber research, previously limited by resource constraints, accelerated dramatically as military leaders recognized that controlling rubber plantations meant nothing if the materials could not reach manufacturing facilities. German synthetic rubber production, initially superior to American efforts, began declining as Allied bombing targeted chemical plants and transportation infrastructure. The Buna facilities that had given Germany early advantages in synthetic materials faced constant air attacks that disrupted production and prevented the improvements that American plants achieved through uninterrupted operation. By late 1944, German synthetic rubber quality had deteriorated while American production continued improving through accumulated experience and technical refinement. The transformation of American tire manufacturing revealed synthetic rubber's broader implications for industrial processes. Tire companies invested millions of dollars retooling production lines designed for natural rubber to accommodate synthetic materials with different processing characteristics. Vulcanization temperatures, mixing procedures, and molding techniques required adjustment as engineers learned to optimize manufacturing for artificial materials that behaved differently from biological rubber in subtle but crucial ways. Consumer acceptance of synthetic rubber tires progressed gradually as performance proved adequate for civilian transportation needs. Early synthetic tires lasted fewer miles than natural rubber equivalents, leading to consumer complaints and dealer skepticism. However, continuous improvements in synthetic rubber chemistry and tire construction gradually closed the performance gap. By 1945, many consumers could not distinguish between natural and synthetic rubber tires in normal driving conditions. The scientific understanding gained through wartime synthetic rubber development opened possibilities that extended far beyond tire manufacturing. Polymer chemistry advanced more rapidly during the war years than in the previous 2 decades, driven by immediate practical needs and unlimited research funding. The knowledge of how to control molecular structures, manipulate polymer properties, and scale chemical processes to industrial levels would enable the plastics revolution that transformed post-war consumer goods and industrial materials. The agricultural applications of synthetic rubber emerged as an unexpected frontier that would reshape American farming for decades to come. Tractor tires manufactured from synthetic materials demonstrated superior resistance to the petroleum-based fuels and hydraulic fluids that increasingly powered mechanized agriculture. Farmers discovered that synthetic rubber tires lasted longer in contact with fertilizers and pesticides that would have degraded natural rubber within months. The chemical resistance that made synthetic materials suitable for military vehicles proved equally valuable for agricultural equipment, operating in environments where biological rubber failed catastrophically. Dr. Wallace Carruthers at DuPont, whose research team had developed neoprene synthetic rubber in the 1930s, found his laboratory overwhelmed with requests from agricultural equipment manufacturers seeking specialized rubber compounds. Combine harvesters required tires that could withstand the abrasive effects of grain dust and chaff, while maintaining traction across varying soil conditions. Irrigation equipment needed gaskets and seals that resisted deterioration from constant water exposure and chemical additives. Each application demanded specific synthetic rubber formulations that pushed polymer chemistry into uncharted territory. The medical applications revealed synthetic rubber's potential in areas completely unrelated to transportation. Surgical gloves manufactured from synthetic materials offered superior puncture resistance compared to natural rubber alternatives, while eliminating allergic reactions that affected some medical personnel. Blood storage bags and medical tubing made from synthetic polymers provided sterile environments that natural rubber could not guarantee. Military field hospitals reported that synthetic rubber medical supplies maintained functionality under conditions that would have rendered natural rubber equipment useless within days. Manufacturing innovations accelerated as American chemical companies competed to develop superior synthetic rubber formulations. The Dow Chemical Company introduced new catalyst systems that reduced production time while improving polymer consistency. Monsanto Chemical developed specialized additives that enhanced synthetic rubber's resistance to ozone degradation, addressing one of the most persistent weaknesses compared to natural materials. These competitive improvements drove rapid technical advancement that benefited all synthetic rubber applications. The infrastructure development required for synthetic rubber production created industrial capabilities that transformed entire regions of America. The Gulf Coast emerged as a chemical manufacturing center as petroleum refineries expanded to supply raw materials for synthetic rubber plants. Pipeline networks constructed to transport butadiene and styrene connected previously isolated industrial facilities, creating integrated chemical complexes that could support multiple industries simultaneously. Towns that had never seen large-scale manufacturing suddenly hosted chemical plants employing thousands of workers in high-skilled positions. Today, every synthetic tire rolling down American highways carries the DNA of that desperate wartime gamble when Japanese conquest threatened to strand Allied armies for lack of rubber. The plants built in frantic months of 1942 evolved into a global synthetic rubber industry, producing over 15 million tons annually, proving that necessity truly mothers invention. When crisis forces innovation, impossible becomes inevitable, and temporary solutions become permanent foundations for industrial civilization.